Forget slow-motion rockets. The future of space travel is here, and it's about to blow your mind. We're talking warp drives, interstellar highways, and a universe ripe for human exploration. Prepare for an exhilarating journey as we reveal how humanity could soon conquer the vastness of space, transforming science fiction into astonishing scientific fact. Right now, almost everything we launch into space still rides on controlled explosions. Chemical rockets are incredible at getting us off the ground and around our cosmic neighborhood. A few days to the moon, months to Mars, years to the outer planets. A crewed mission to Proxima Centauri with today's technology would take tens of thousands of years. And because nothing with mass can reach, much less pass, the speed of light, the galaxy starts to look like a museum we can only observe from behind the glass. This is where the famous Fermi paradox kicks in. If the universe is full of stars, planets, and potentially habitable worlds, where is everybody? Why don't we see clear signs of advanced civilizations crossing between the stars? One harsh answer is that almost nobody manages to solve the interstellar problem. If we want a different fate, we can't rely on slightly better rockets. We need new physics, or at least new ways of using the physics we already know, to bend the rules of the game. The good news is that pushing boundaries is something our species does well. We've crossed oceans, climbed into the sky, left footprints on the moon, and landed robots on other worlds. The same restlessness that made our ancestors follow unknown stars across the sea is now aimed at real stars across the galaxy. We don't just want to watch the universe from a distance. We want to visit it and, one day, live in it. To do that, we have to stop thinking only in terms of engines and start thinking in terms of space-time itself. That's where one of the strangest ideas in modern physics appears: the Alcubierre warp drive. In the 1990s, physicist Miguel Alcubierre took Einstein's equations of general relativity and asked a provocative question. Could you, in theory, move faster than light without actually breaking the cosmic speed limit? The answer hidden in the math was surprising. The speed of light limits how fast objects can move through space, but it doesn't limit how space itself can move. The universe already stretches so quickly in some regions that distant galaxies appear to recede faster than light, and physics is fine with that. The warp drive takes this idea and turns it into a starship concept. Instead of pushing a ship through space, you wrap it in a bubble of distorted space-time. Space in front of the bubble contracts, space behind it expands, and the ship rides safely inside that wave. Locally, you're almost at rest inside the bubble, so you never technically break the light speed limit. But from the outside, the bubble itself can cross light years frighteningly fast. To an observer watching from Earth, it would look like you left our solar system and popped up near another star faster than light ever could. On paper, it's all perfectly legal according to general relativity, which is why scientists took the idea seriously enough to study it. Small teams at NASA and other institutions have explored modified warp bubble shapes that might reduce the energy cost and have looked for tiny, lab-scale, warp-like effects. Early estimates demanded more energy than exists in the observable universe for a ship the size of a house. Later refinements lowered that number, but we're still talking about the mass energy of planets or stars. Worse, the warp bubble seems to require exotic matter with negative energy density, something we've only seen in subtle quantum effects, not in any form we could shovel into a reactor. So for now, the Alcubierre drive sits in a strange zone between impossible and not strictly forbidden, like a lighthouse we can see but have no path to reach. And it's not alone. General relativity also allows for wormholes, tunnels through space-time that could connect two distant points almost instantly. In theory, you could step into a wormhole near Earth and emerge near another star, skipping the long journey in between. But the most promising models also require negative energy matter to keep the tunnel open. Without it, the passage collapses too fast for anything macroscopic to cross. Quantum physics adds its own touch of weirdness. Quantum entanglement, Einstein's spooky action at a distance. links particles so that measuring one instantly affects the state of the other, even if they're light years apart. It sounds like the perfect faster-than-light communication system, but there's a catch. All our experiments and theories say you can't use it to send usable information faster than light. Still, it hints that there may be deeper layers of connection built into the universe. If future physics ever finds a loophole, it could transform how we talk to distant ships and probes, even if we never outrun light itself. Of course, there's also a more down-to-earth strategy. Accept the speed limit and design our journeys around it. That's the idea behind generation ships. Imagine enormous self-sustaining spacecraft where entire communities live, work, and raise children while the ship glides along at a fraction of light speed. The ship is both home and journey, a moving city carrying human culture between the stars. It may not be as spectacular as warping across the galaxy, but from a purely physical point of view, it could be one of the most realistic ways to spread humanity beyond the solar system. While all of that belongs to the far future, the next steps toward the stars are already being sketched. Nuclear thermal rockets would use a reactor to superheat hydrogen and blast it out of the engine, roughly doubling the efficiency of chemical rockets and cutting travel times around the solar system. Go a step further, and you reach nuclear fusion rockets, powered by the same reactions that light up the sun. Compact, reliable fusion would let ships cruise much faster without hauling absurd amounts of fuel. We still wouldn't reach warp speed, but the outer planets and even the distant Kuiper belt would finally fit inside a single human lifetime. Then there are concepts that barely need onboard fuel at all: solar sails and laser sails. Picture a spacecraft attached to a huge, ultra-thin, reflective sheet. Sunlight pushes gently on the sail, and over time that push adds up, slowly but steadily accelerating the craft. Replace sunlight with powerful lasers fired from Earth or from space stations, and a very small, very light probe could be pushed to a significant fraction of the speed of light. Ideas like this are already being seriously studied as candidates for the first true interstellar probes humanity might launch. Whatever technology carries those probes, one thing is almost certain: our first visitors to other star systems probably won't have heartbeats. AI-controlled robots don't need air, food, or gravity. They can sleep for decades, wake up near their target, map planets, analyze atmospheres, and beam the results home. As artificial intelligence and miniaturization advance, we'll be able to build swarms of smart, lightweight explorers that can go where it would be too dangerous, too expensive, or simply too slow to send humans. All of this effort, from warp drives on whiteboards to fusion engines on drawing boards, points to a deeper question: why does interstellar travel matter so much? The first answer is survival. Earth is beautiful but fragile. Asteroid impacts, supervolcanoes, climate shifts, or even our own technology could make life here much harder. Becoming a multi-planet civilization, and eventually a multi-star one, spreads the risk. The more worlds we inhabit, the harder it becomes for a single disaster to erase our story. The second answer is curiosity. We already know of thousands of exoplanets, and we're just scratching the surface. Others are truly alien. Super-Earths with crushing gravity, frozen spheres hiding deep oceans, or gas giants with storms larger than our entire planet. Visiting them, even with robotic probes, would rewrite our textbooks and transform how we see planets, atmospheres, and maybe even biology itself. If we ever find a single microbe in an alien sea, or ancient fossils in the rocks of a distant world, it will change our understanding of life and our place in the universe forever. And finally, there's what all of this says about us. Every time we push beyond what seems possible, we prove that imagination and curiosity are some of humanity's most powerful engines. Today, warp drives, wormholes, and generation ships live mostly in theories, labs, and science fiction, just like airplanes and reusable rockets once did. Maybe the first warp bubble will never ignite, and our path to the stars will be slower, carried by fusion engines, shining sails, and patient generation ships. Or maybe, somewhere in a quiet lab right now, someone is taking the first tiny step toward bending space-time on command. One way or another, the journey has already begun, because we're daring to ask the question. And if you want to keep traveling on the edge of what's possible, exploring black holes, alien worlds, and the future of our species among the stars, make sure you subscribe, leave your like, and share this video. The more curious minds we bring on this journey, the closer we get to turning the impossible into our next destination. Thank you. See you next time.